This video summarizes the first introductory chapter from my new Scalable Planning book, explaining what the book is about and what I intend you to get out of it. My intention is ultimately to produce a short video like this one for each other chapter as well. There are also other resources such as a blog at alipar.com. Simply put, the book presents a way to develop and think about a plan, such as a computer program or a large organizational plan, to best exploit whatever available physical resources can be devoted to help execute it. It is for cases where the planner has a fixed set of resources, but also if the planner doesn't know what those resources may be when the plan is being constructed, and even if the quantity of available resources may vary while the plan is being executed. The ability to effectively use varying quantities of resources is called scalability, and when the plans are computer programs and the resources are processors or cores, the ability to get many working on it at once is often called concurrent or parallel programming. The same techniques described here are also useful for understanding how different parts of a single device can operate together to perform a task. Generally speaking, most people are already familiar with sequential planning, such as following or constructing algorithms, programs, or recipes. A sequential plan like that proceeds in a series of steps, one at a time. Do this, then do that, and if this other thing happens, do this a few more times, otherwise take care of this other thing. Cooks and traditional computer programmers live this sort of planning. That works fine when one entity, such as a person or computer, is executing it. It's also straightforward to get multiple entities working at the same time, each on completely different independent plans. The trick is to get multiple entities working together to execute a single plan. For that, the issues start getting tougher. A common approach is to construct the overall plan of smaller parts, each being itself a plan that one entity can handle on its own, plus instructions on how the littler plan should communicate and or otherwise coordinate to get a solution together. Now, concurrency isn't always the answer to getting a speedy answer, either because the additional time and overhead of the communication and coordination overwhelms getting productive work done, or because the effort of formulating the plan for multiple entities itself is too onerous. Generally speaking, concurrency pays off more often for larger problems that take more time to solve. But getting the correct result is still important. As the old adage goes, if I had known you didn't care that the answer was correct, I could have delivered it much quicker. Obviously, we want a concurrent plan to possess several desirable properties. Here are 7 important ones. Sequential consistency. Even if we want multiple entities to be able to carry out a plan concurrently, it should also be possible for just one entity, that is you, to devise the plan and ensure that it is correct, to figure out how it will possibly behave once other entities are put to work on it, and to understand how it has behaved after the fact, and all without doing anything superhuman, like keeping many things in your head at one time. In other words, it should be possible to analyze how it will all work together one step at a time, even though it's concurrent. Another property is platform independence. When a collection of entities, sometimes called a platform, work together on a plan, they typically need to communicate, and how they communicate depends on the modes of communication that are available, and those in turn often depend on how far apart the communicating entities are and or what kind of communication medium connects them. Common modes of communication include sharing, like via whiteboard or shared memory when the entities are relatively close together, and passing messages when they are relatively far apart. We want to construct our plans that are independent of the mode and or medium of communication available so that those plans will work well on any kind of platform. Another property is latency tolerance. When entities for example, must be far apart, communication can take time, which is called latency. Ensuring that a plan can keep busy while communication is occurring is called latency tolerance. Generally speaking, the more concurrency in a plan, that is, the more parts it is built from, which can act together, the more chance that some of them can be kept busy while other parts are waiting for communication. Another desirable property is called scalability, with variable granularity. Just as with latency tolerance, ample concurrency is also imperative in making a plan capable of making use of many entities available to help carry it out, scalability. But sufficient concurrency isn't enough for scalability. That also requires that if there are only a few entities available, or even one, that having the plan broken down into lots of little pieces doesn't actually slow things down because of all the go-nowhere communication occurring between those pieces. The ability to make the overhead of communication go away when communication is not needed is called variable granularity. Another desirable property is that it be well engineered. People like software engineers, who have been dealing with large complex sequential plans for decades, have developed useful techniques for developing them and helping to ensure that they're correct. These techniques include structured programming, object-oriented principles, and debugging techniques. In the last few decades, parallel programmers have also developed some techniques for attaining concurrency, such as data parallelism and divide and conquer approaches. Since programs are examples of plans, we would like to take advantage of all these decades of experience. Another desirable property is tameability with respect to non-determinism. Since a concurrent plan does not specify a single sequence of operations, some of the operations can occur at the same time, or perhaps in different orders when the plan is being carried out. And depending on what the operations are, the order of those operations may affect the result. So some plans may produce different outcomes even when executed with the same initial conditions or inputs, unlike sequential plans. This property is called non-determinism and is not always desirable or intentional. In fact, trying to track down what happened can itself cause that same thing not to happen again. We'd like to make sure that any non-determinism that is present is only when intended, to understand its possible effects when it is present, and to be able to determine what happened after the fact when it behaves in unexpected ways. And yet another desirable property is fault tolerance. The more entities that are involved in carrying out a plan, the more extensive or complex the communication medium between them, the more likely it is that something will go wrong. If that happens while carrying out the plan, we need a way to keep as much of the work that's been done without starting over from scratch. That property is called fault tolerance. Rather than focusing on traditional ways of addressing these properties in a piecemeal fashion, this book uses a relatively novel visual approach called Scalable Planning language, or Scalpel for short, to address them all together in one cohesive representation, consisting largely of annotated circles, lines, and boxes. Scalpel can be regarded as just a teaching tool, or if you prefer, a full-out language for developing plans. Scalpel has been developed over decades, starting with an approach called large-grain data flow, which evolved into software cabling before becoming Scalpel. The theoretical, formal, axiomatic basis for Scalpel is called FNets, or function networks, which you can learn about if you like in one of the chapters. For those familiar with atomic transactions, Scalpel and FNets are based roughly on a slightly extended version of those, called actons. Since all behavior is built from those pieces, the approach is generally called elemental concurrency. So why is this work especially salient now? Well, for cases when the entities involved are people, a communication explosion is occurring with cell phones, etc. We are now constantly connected with each other and with computer services at our disposal. This naturally introduces the opportunity for concurrency and problem solving. And when the entities are offices, or divisions, or organizations, it fits with the increased teaming and offshoring of commercial work going on these days, sometimes described as flattening the earth. And when the entities are computers, this work is especially compelling, due largely to the course correction that occurred in the new millennium. Until then, owing to increased device density driven by Moore's law, processors were speeding up every year, so if you wanted your application to run faster, you could just wait till next year, at which time you'd probably add more features or resolution or something to eat up the additional computer power. But around 2000, chip designers hit a wall. The amount of power it was taking to feed and cool each processor simply became untenable. So even while transistor density kept going up, the speed and power of the processors leveled off. Instead of making each processor faster year after year, designers started adding multiple cores or processors to each chip, so the power and speed could increase linearly. The drawback, such chips would yield speed improvements only if programmers could make use of those extra cores. So nowadays, your application does not just naturally go faster on next year's chips than it did on last year's, unless you've programmed it to benefit from the available concurrency provided by those extra cores. Also, through the decades, various coprocessors have been developed to handle specialized tasks until or unless their functionality has eventually been integrated into mainstream processors. In past decades, these have included floating point and array coprocessors. More recently, graphics processor units, or GPUs, have been common, and now are being relied on for some central computational tasks instead of just for graphics. In all of these cases, there is not only an opportunity for concurrency between the coprocessor and main processor, but also a desire to construct programs in a way that enables but does not depend on their use, a specific case of platform independence. And more recently, cloud computing and grid computing have also been on the rise. In these, a huge hidden distributed platform supports drastic amounts of concurrency and storage. Cloud computing relies primarily on the storage and a fixed set of applications. Grid computing generally extends that idea to support almost arbitrary applications and interaction with devices and humans. So yes, understanding concurrency and its issues is becoming more salient every day. The Scalable Planning book isn't your typical parallel programming book, but it's built with that use in mind. If you don't know anything about programming, that's okay. It introduces all the terminology and avoids too much lingo. But if you're using it to teach or self-learn parallel programming, you should ask yourself, should concurrency concepts be taught the same way they were 30 years ago? Programming curricula these days rarely start with machine language and assembler. Should today's parallel programming curricula be saddled with their analogs, message passing, semaphores, and locking? Here my answers are no. There are chapters to cover the lower level mechanisms if you want to go there, but the focus here is on higher level concepts, on constructing correct, portable, understandable, efficient programs and plans, leaving the low level details to others. As a result, it is organized much like other sequential programming texts, with chapters on topics like structured programming, object-oriented principles, arrays and dynamic resource allocation, and formal methods, but in a concurrent context. So, to sum up, this book is forward-looking. There is no telling exactly how the future will unfold, but there is a consistent set of principles involved, and anyone experiencing and/or planning concurrency from a personal, organizational, or computational viewpoint will benefit from understanding them and some techniques for dealing with them. That is the goal of this book.